Look
You've
at the
pulled a plug out of a
uniformity here.
wall
There's
socket
no stress
thousands of
fracturing
times in your
around the
life.
collar.
Recording
Yet you've
that.
probably never
The
examined
degradation
it closely.
stops precisely at
Two
the hole's
flat metal
boundary.
prongs, and near the tip of each one, a tiny round hole, just a few millimeters wide, so small that compared to your pinky fingernail, it's less than half the width. Some people say those holes help electricity flow faster. That's like claiming highways need windows so the wind can pass through.
100 years in
Electrons
this
don't care
environment, and
whether
these
there's
holes
a
are
hole
pristine.
or not.
Look at
They
the data
move
from the
according
laser
to
profile.
voltage.
The edges
Not
are almost
architectural
perfect.
style. So what's the real purpose? Why would such a small detail requiring extra machining remain in place for over a century without being removed?
The erosion
answer
rate
isn't
doesn't
purely
match the
electrical.
surrounding stone.
It's
And the
mechanical.
internal structure is
It's about
perfectly
friction.
preserved.
About a
We need
faint
more
click
samples.
you rarely notice. And about the fear of electrical sparks. Inside a standard 120-volt North American outlet, the familiar household type in the United States and Canada, are two contact strips made of copper or copper alloy. Copper is chosen because of its low resistivity. About 1,68 mal 10 hoch
The
negative,
copper
8
contact
Ohm,
strips are
meaning
essential
electricity
for
passes through
safely
it with minimal
conducting the
resistance.
current within the
much
outlet.
like water flowing through a wide pipe. When you insert a plug, its metal prongs slide between those contacts. What many people don't realize is that numerous outlets are designed with small internal bumps or metal tabs. As the prongs reach their final position, these tabs snap into the round holes. The sound is subtle, not like locking a door, but enough to create mechanical retention. If you accidentally kick the cord, a force of just a few newtons, similar to the gentle push of a book falling from a table, the plug doesn't immediately slip out. This mechanism works like a seat belt. It doesn't prevent all movement. It keeps things stable during sudden disturbances. As a result, the plug exists in two clear states, fully in or fully out. Not halfway, not loosely touching. And that distinction is crucial for electrical safety. A loose electrical connection creates what engineers call contact resistance. When two metal surfaces aren't pressed firmly together, the actual contact area shrinks to tiny microscopic knockout. Electrical current is forced through these small spots, much like water squeezed through a narrow nozzle. With 120 volts and several amperes of current, for example,
and a significant fire
a
hazard.
1,200 watt hair dryer, drawing about 10 amperes, the heat generated at those contact points can rise quickly. Power dissipation increases with the square of the current. Double the current, and the heat quadruples. High heat combined with a small air gap can lead to electrical arcing. An arc occurs when electricity jumps through air, where the voltage becomes high enough to ionize air molecules. Normally, air is an excellent insulator, but once ionized, it briefly becomes conductive. That spark doesn't just erode metal, it creates a fire risk. Electrical fires caused by loose household connections have been documented since the early 20th century, when insulation materials were far more primitive. The round hole in the plug prong, working together with the retaining tab inside the outlet, helps maintain consistent pressure. That pressure increases the true contact area, reduces contact resistance, and lowers the likelihood of arcing. A tiny detail, but one that directly affects heat, friction, and safety. Once you understand that, you start seeing a plug not just as a conductor of electricity, but as a mechanical structure. The story doesn't stop at safety. In industrial manufacturing, every detail must answer one question: is it worth existing? A round hole, roughly 3 millimeters in diameter, removes a small amount of metal. If each prong weighs a few grams, the removed material amounts to only fractions of a gram. It sounds insignificant, but multiplied by billions of plugs produced worldwide each year, that tiny subtraction becomes hundreds of tons of copper.
This
Copper
cutaway
isn't as
view
rare as
demonstrates
gold,
how the flexible
but it's
retaining
still a
tab
valuable
locks into the
resource,
groove, maintaining
traded on global
consistent
markets at
contact pressure
thousands of
within the
dollars per
housing.
ton. On production lines, those holes also serve as anchoring points. When molten plastic is
contact pressure
molded
is
around the
unstable,
metal
intense
prongs
arcing
to
occurs.
form the finished
However,
plug,
with stable pressure, the
machinery can insert pins through the holes to hold the prongs firmly in place. The hot plastic flows around them without shifting their alignment. For electricians, the round holes can act as attachment points for probes or alligator clips during quick testing, reducing the chance of slipping. One small feature serving mechanical stability, safety, and manufacturing efficiency at the same time. Then there's the inertia of standards. When hundreds of millions of outlets have already been manufactured to match this mechanism, removing the holes would mean redesigning an entire ecosystem. In engineering, the longest-lasting solutions aren't always perfect. They're simply good enough and deeply integrated with everything around them. The next time you plug in your phone charger, take a closer look at those two small holes. They don't make electricity move faster. They aren't there to let the plug breathe. They exist because of friction, electrical arcs, manufacturing processes, and a century of standardization. Small details like this surround us. A tiny groove on a bottle cap, a notch on an ATM card, a ridge along a stainless steel spoon. Each carries a hidden logic. If you enjoy dissecting design like this, we can keep going, examining the seemingly meaningless details that quietly control entire systems. Just pick an everyday object
from steam power
and
to
start
aerospace,
peeling
the
back
fundamental
the
standards
layers.
remain.